Yeah, you have to hit got it on your screen here.
I can't hit got it. Let's see who it's good. So there we go.
Okay, so we're very happy to have Michael Peskin here. He's a very distinguished high energy theorist who's been at SLAC for a long time. He was a student of Ken Wilson's, and Wilson achieved a higher honor than Nobel Prize, which is that his last name is commonly used as an adjective by high energy theorists, Wilsonian. Yeah, it's one of the only 20th century physicists to reach this. Yeah, so Michael's won many awards. He's a member of ATS and both double, triple A. He founded a subfield we call now electric precision tests of using calculations in QFT and precise measurements at colliders to indirectly infer things. So 20 years before the Higgs was discovered, he showed that an alternate idea where there would be no Higgs called Technicolor was disfavored by data at that time, and it kind of predicted that it would be discovered later. And now there's a whole field of people working on similar methods applied to higher energies. And when I was an undergrad, he mentored an undergrad project for me, which was very nice at Stanford. So he had me computing things in an extra-dimensional model that probably didn't exist, and then testing at a collider that didn't exist, and I was totally hooked. So I think that's what got me into particle physics more than anything else. Yeah, and he wrote the book that like several generations of us learned QFT from.
Okay, well, thank you very much. There's something I have to object to in your introduction, though.
I'm sorry?
Because I only looked at the beyond standard model part of precision electronics. That was, a decade after the founders actually founded that subject. And one of the big founders is Alberto Serlin, who we're going to celebrate tomorrow. So please come to the festival tomorrow, and we'll learn all about the work of Alberto Serlin and how we're trying to bring that forward into precision. So, yeah, I don't take much credit for that.
Yes,
okay. The other stuff I'll take. Okay. So let's see. So here's the title of the lecture, which you've all seen. And what I'd like to do is it's a colloquium. I'm going to talk to you probably in quite general terms about the current status of high energy physics as I see it. And in particular, actually, I'm going to talk to you not about the next machine, but about the next machine after that. So we're really talking about long-term goals in particle physics. And I hope you'll find this intriguing enough to follow it as we start what's really the next crusade to try and learn more about the fundamental equations. So I think the first thing that I have to say to an audience that contains a lot of condensed matter physicists and people from other fields is that we're all doing physics, but particle physics is really different in a certain way. You write nonlinear equations, amazing things happen. And this is true both in classical and quantum mechanics. And so there's an enormous variety of phenomena that you could study in physics. And I have two of the more amazing things here. So this is the Kármán vortex street that you have in a high Reynolds number flow. And this is the structure of YBCO, one of those high temperature superconductors. And these are all both still active areas of research with many ramifications and many applications. High energy physics is really different. In particle physics, we're not interested in all the various ramifications of the equations that you have as effective theories. We're only interested in one set of equations, namely those that provide the fundamental grounding for all the laws of physics. And so this leads us in some sense, certain crazy directions. Why do we want to know this? Well, it's generally not motivated by immediate applications. It's motivated by basic curiosity about the origin of everything. We're very interested in the ultimate unification of all interactions. Of course, we interact with the other fields of physics. I think we have an important benevolent influence. As a theorist, I would say that this problem of finding the truly fundamental interactions, it's a very subtle problem, but it has a lot of unexpected symmetry. And that's brought ideas into the rest of physics that have been very useful. Probably the normalization group is the principal one of those. And also, it's a tremendous technical challenge. And it's a source of technology for other fields. So I certainly remember back in the 1980s, the debate about whether one should put money into building a superconducting super collider or spreading it around condensed matter physics laboratories. But since then, we have the X-ray synchrotrons, the spallation neutron source, the free electron lasers, all of which basically are outgrowths of people's attempt to solve this problem of how do we get to higher energies. And so I hope you'll be interested in what we're trying to learn. I hope certainly you'll be interested in what we're going to produce as we try and learn it, because this is an extremely difficult problem. And the other thing that I'd like to say is that this is a problem that plays out on a very large scale. So we've organized the largest and most expensive pieces of scientific equipment, the largest collaborations of physicists, and actually at the LHC, the largest experimental databases in science, although I think we still haven't rivaled the Google database. We're up there. The discovery of the Higgs boson was a 45-year quest. 45 years after it was postulated, tens of billions of dollars spent, 6,000 physicists signing the original discovery papers. So the things we do somehow take on the role of a kind of crusade. And I guess what I want to talk about today is, well, now that we've discovered the Higgs boson, what's the next crusade? And maybe in 45 or 50 years we can solve this. But as I'm a theorist, it's fun to start thinking about that now and try and start the community thinking about what are really long-term goals. So, of course, we're interested in, quote, fundamental interactions. That is, interactions that occur at extremely small distance scale. And part of the problem is that as we search for these interactions, we get further and further from the human scale, which is what requires all of this largeness in personnel and technology and sophistication of that sort. So let's talk a little first about how far we have come. And I just wanted to give you a few examples of recent, maybe some not so recent results from particle physics. So I've written here the Lagrangian of what we call the standard model of particle physics. So this, as we understand today, is an extremely accurate representation of our knowledge of the strong, weak, and electromagnetic.
Do you hear, or am I on Bluetooth? No, but do you hear what the lecture?
I'm sorry.
I'm on Bluetooth.
Eliezer, we hear you even too well.
Out there in Zoom land, can I be heard if I stand here, or do you want me to stand closer to the microphone?
They should be able to hear.
We can hear you, Professor.
Okay.
Yep, we can hear.
Okay. So this Lagrangian contains a large amount of gauge symmetry. There are actually 3 gauge symmetry groups contained in it. Those are coupled to fermions and also the gauge particles themselves through the covariant derivative, which you see as capital D. This equation really summarizes an enormous amount of physics. And in fact, to use it, you also have to understand even more physics, because it contains the phenomenon of spontaneous symmetry breaking of some of these gauge symmetries, confinement of quarks, et cetera, et cetera. It's certainly not as simple as it could be, but it's not so bad if you want to summarize, truly all of the equations that we see at microscopic scales. And as I said here, this set of equations alone will keep nuclear, condensed matter, fluid, optical physicists occupied for centuries. So you can ask why we want to go on, but of course, we're us. We want to go on. So, but first, let's talk a little about what we know about these equations at the basic level. The couplings of all particles are guaranteed by something called the gauge principle, which says that the coupling is through the covariant derivative. something you folks all learned about in quantum mechanics, and here we expand it to the non-abelian symmetry groups that appear in this model. And so this includes many non-trivial features which are now verified in detail by experiment. So let me just show you 3 of those. The first one is this measurement of the line shape of the Z boson. The Z boson is one of the basic particles of the weak interactions. It mediates the so-called neutral current decays. Ordinary beta decay, which produces an electron and a neutrino, is a charge current decay. There's also the possibility that the weak interactions can produce E plus E minus, let's say, or E plus E minus can turn into a weak interaction final state. And so that's mediated by this particle called the Z boson, which appears as a resonance in electron-positron annihilation at a collider. What's interesting about this curve is that the black curve is a 1-parameter theoretical prediction within the standard model. And the little red dots are the data. Can you in the back see the red dots? Okay. This contains actually all 3 of the fundamental interactions. It contains electromagnetism because as the electron and positron annihilate to produce this resonance, they radiate photons. And so that gives rise to the noticeable asymmetry of this curve toward the higher direction. Of course, it's basically a weak interaction phenomenon, but also you have to understand the weak interactions at the higher loop level in order to get this level of accuracy. And finally, the decays to quarks involve radiations of gluons. So the gluons broaden this curve by 3 or 4%. And unless you include that effect, you can't make this work either. So the whole model is actually tested in this curve. You can test it in many different ways. Here's another example. This is a set of cross-sections measured by ATLAS, one of the detectors at the Large Hadron Collider, of various processes. And you see there are various processes here. This is it's a proton-proton collider. So this is PP production of jets, single gammas, single W bosons, Z bosons, etc., out to very complicated final states. The dots are the theoretical predictions, sometimes with little gray error bars. The bands are the experimental predictions from the ATLAS and CNS experiments, I guess. Oh no, from different energies. It's all from ATLAS. What's interesting especially are these towers. So when quarks come together and form, for example, in this tower, a W boson, they also radiate gluons. And so there's a theoretical prediction for the radiation of 1, 2, 3, 4, 5, 6, 7 gluons. Those depend in increasingly complicated ways on the nonlinear structure of the strong interactions. And it works. Here is the column for the Higgs boson. And there, what you're seeing are the predictions for the various Higgs boson decays. We'll talk about that a little later. So there's a wealth of sophistication in this plot when you go down the columns. And so far, the standard model seems to be getting it extremely right. So this tests the fundamental couplings of quarks, gluons, electrons, etc., at a very deep level. And finally, this is the plot of the various probes of flavor mixing and CP violation in the weak interactions. The data here comes from the Babar, Bell, and CDF experiments compiled by this group called the CKM Fitter. The individual measurements are these bands. CP violation means that you're not on this axis, on the horizontal axis, but you're up here at some non-zero value of, if you like, the imaginary part in this plane. The fact that all the curves pass through a single point or region is totally non-trivial. And it really is, again, the structure that all of these mixings are coming just through basically a few terms in the interactions of W bosons with quarks. So this is all something that we understand extremely well, and it's really a key understanding of this whole set of forces. Now, the gauge principle, however, has an unusual property, which is that it forbids mass for all of the force-carrying particles and all of the matter particles, quarks and leptons. And in order to remove that and allow these particles to have mass, you have to somehow break the symmetry, which is an underlying principle of this. And of course, we learned from condensed matter physics about how to do that. You have spontaneous symmetry breaking. So you have some field which can serve as an order parameter, and then you somehow arrange a potential that the minimum energy situation has that order parameter having a zero value. And the field that carries that order parameter is called the Higgs boson. This is this thing that I said before was at the center of the standard. So for example, the electron mass in this model can't arise from a term E bar E. It arises from a term that involves the Higgs boson. Only this structure is symmetric under all the basic symmetries. But then when the Higgs boson acquires an expectation value in the ground state of the Hamiltonian, this is replaced by a number and the electron mass turns on. And there's a relation between the electron mass and the coupling constant that appears here, which is called the colloquium. This is a spontaneous breaking, which is similar to many instances of spontaneous symmetry breaking in condensed matter physics, in superconductors and magnetism, etc. Now, there's a prediction of this structure, which is that the masses are directly proportional to the Euclid couplings, given the proportionality of this expectation value. So if you can measure the masses and the Euclid couplings independently, you can test this relation. And that's actually what's been done. Actually, maybe I should say there are two consequences. The first is that since the Higgs couples to everything, there are many different decay modes. So there are actually 10 decay modes predicted for the Higgs boson with branching ratios greater than 10 to the minus 4. We've now observed 5 or 6 of those. Also, the Higgs couplings are proportional to the measured masses. So if you measure the decay widths, you can check that. And so here are just some examples. Here is a Higgs boson event that was measured in Atlas. The Higgs, which decays to 2 Z bosons, the Z bosons can decay to a muon pair and an electron pair. And you could visualize that in the detector. And you see that here. The very penetrating particles are the muons. The particles that are stopped by the electromagnetic calorimeter, these two stubs, or the two yellow things here, are the electrons. The total mass is 124.3 GeV. Of course, with measurement error, this fluctuates around what we now know is the right value, close to 125 GeV. The relation between the masses and the Euclid couplings is shown on this slide. So on a log scale, you see it's just incredible. Maybe if you put this on a linear scale and really look at the deviations, there are 10 to 20% deviations, but it's still incredible. And the spontaneous symmetry breaking mechanism really does account for the masses that we see. Okay, so what's the problem? We seem to understand all of this stuff extremely well. Well, there are many different high energy physicists will point to many different aspects that are problematical and cite different problems as the problem. But of course, I've got my own opinion about that. And in my opinion, the key problem is that we understand all of these things I've shown you phenomenologically. For the gauge boson couplings, muon, W, and Z, and photon, we have an underlying explanation, which is the presence of the gauge symmetry, which really fixes those couplings. But for the Higgs boson, we really don't have any understanding at all. We have various possible couplings, which we fill in by fitting them to experiment. So for example, these Y couplings that I showed you for the electron, we know what they are because we know what the electron mass is, but we don't know why they are what they are. For example, why do the fermions have such a wide mass spectrum, from half an MeV for the electron to 170 GeV for the photon? We know that there is the possibility of CP violation in these couplings, but we don't know why that should be there, where it comes from, how to calculate it. And so that's a question which is galling just in the abstract, but it's even more galling when you compare it to what we know about condensed matter physics. Because in condensed matter physics, whenever there's a spontaneous symmetry breaking, there's a very interesting story behind it. For superconductivity, the Cooper pairs. For magnetism, we have Hund's rule. Magnetism really is very complicated. It occurs only in specific regions of the periodic table, and we understand that now from the underlying physics of the overlap of electron orbitals. For liquid crystals, we're talking about molecules that have unique shapes that like to orient themselves one to the other. Well, it'd be nice to have a story like that about the Higgs boson. But right now, all we know about the sector that produces the spontaneous symmetry breaking in this model is that we know one particle in it and all of its constants, all of its couplings, all of its properties. We just fit them from experiment, and we don't know what the underlying story is. So an analogy that I'd like to make about this is to the history of superconductivity. In superconductivity in 1950, Landau and Ginzburg wrote down their beautiful phenomenological theory. And it's a very powerful theory. It predicts the thermodynamics of the phase transition, the Meissner effect, the critical current, the existence of type 1 and type 2 superconductors, and the Abrikosov flux tubes and flux state. But what it doesn't explain is why supersymmetry occurs and why superconductivity occurs in the first place. For that, we had to wait another 7 years and a whole different set of physics until BCS discovered the Cooper pairing mechanism and the unique ground state that comes from it. And so in particle physics, we're still at the Landau-Ginzburg stage. We have this great phenomenology that predicts a lot of things, but no underlying understanding. And nothing from which we can, like from more fundamental principles, compute the couplings of things. So this question implies that there are new particles and interactions beyond those of the standard. There are various hints about this, but those hints, they're not very, if you say they might be persuasive, but they don't really point in a certain direction. One thing that is often said, and I'd like to say it here, is that if you try and compute the corrections to the Higgs mass, so you remember in spontaneous symmetry breaking, it's often the question of whether the potential is shaped with a minimum at the symmetric point, or if you put a negative mass squared parameter, whether that's a maximum and the minimum of the potential is somewhere else. That receives radiative corrections in the standard model. Here's a typical example where you have the Higgs boson out here, coupling to the top quark, and you compute the loop of virtual top quarks. If you compute this diagram, it turns out to be infinite, proportional to the top quark you call a coupling. This is okay for phenomenology because the standard model is a renormalizable theory. So renormalizability says we can't compute all the parameters. We'll fix some from experiment. But this is a particularly galling one to fix from experiment because it really tells us literally you can't understand why this occurs. If we had new particles, we could perhaps find some other particles that would cancel this infinity and give a finite answer. And if we could do that, then we'd have a basis for doing calculations. And probably if we understood about those particles, we'd really understand a lot more about the Higgs and its accompanying particles that we do. So how do we get that information? Naively, you would say, well, the top quark has a mass of a couple hundred GeV. So probably if this diagram is rendered finite, that's where you would expect the particles that also combine with this diagram and make it finite. That's what people believed before the LHC turned on. But unfortunately, we've been quite disappointed. These particles, predicted by many different models, have been searched for intensively at the Large Hadron Collider. And so far, none of them have been seen. I think I have a couple of slides here on searches. This is the searches in Atlas for the top quark partner. So this is what it's supposed to decay to. This is the mass of the partner itself. It depends all on the various parameters. This is a supersymmetric theory, so it depends on the parameters of the supersymmetric model. They go out when this daughter particle is very light, they go out above 1 TeV, which is really well beyond where this particle was expected to be found. I think Josh Ruderman played a big role in figuring out how to fill in this region here, where the supersymmetric partner has a mass roughly equal to the top quark itself, which is experimental in quite itself. Anyway, nothing turned up. Another kind of particle that I like very much is a heavy quark, which would be a partner of the top quark. And this is an atlas search for those particles. These little boxes are the searches at different masses, up to a mass of, well, I guess you really have results now, up to about 1200 GeV. The different colors are searches in different final states. So the mixture of final states is expected to be in this triangle here. And as you can approach it from different corners by looking at different possible decay products. But again, these are exclusions, and the white areas are things where the exclusion just isn't powerful enough because you don't produce enough events to access that mass. But I certainly expected discoveries in this region here, and that's now pushed to higher energies. So the ideas that are now seriously challenged by the LHC exclusions are, first of all, supersymmetry, at least in its simplest manifestation. You could always imagine tuning the parameters to push up the masses of the supersymmetric particles, but this becomes more and more unfavorable as you have to push further and further. Also, composite Higgs, certainly the idea of Higgs as a simple QCD-like bound state, looking like the Higgs particle is some kind of hadron of new interactions. It's more and more difficult to accommodate that with the things that I put on the second of these things. You could rescue these by fine-tuning. This is something that we call the little hierarchy problem. But maybe that's not as interesting as having some physical mechanism that does this. But unfortunately, the physical mechanisms also bring in models that are quite complicated. People talk about the Higgs being a Goldstone boson of some symmetry breaking that occurs at a much higher mass. Probably the right place to put that mass, consistent with electroweak constraints, is somewhere around 10 TeV. Then sequentially, you would break symmetries until finally the Goldstone bosons discover that the symmetries that make them massless are not quite correct. And there are models like that, but they, I think, generally people in the field don't find them compelling because of their complexity. And to make those models come into reality, we would have to find some of the ingredients realized in experiment. There's a concept called Dirac gauginos that Neil Weiner has contributed to. There, you extend supersymmetry, so you have a higher supersymmetry at, let's say, again, about 10 TeV. And then sequentially, supersymmetry is broken in stages until finally it gets to the Higgs boson 2 orders of magnitude below. So there are a number of schemes that look like this, which are, if you like, they're intellectually more appealing because they have more explanatory power. But on the other hand, they're, well, what I say, it doesn't grab your heart because the models are quite complicated. And so we're kind of caught between these two. The simpler ideas that you have to fine tune for some reason that we don't understand, the more complicated ideas, which where you can really make models, but unfortunately they're complicated with many parameters, and again, they lose their validity. What we really need is an experimental discovery, and to do that, it may still happen at the LHC. But I think in view, especially of the things that I've listed here, where the model develops in stages from a very high energy to the 100 GeV scale of the Higgs boson, we really have to start thinking seriously about going to much higher energy than we've been able to achieve so far. I wanted to put this in here just again as a change in this culture in our field. In the early 90s and even into the 2000s, it was thought that you could have supersymmetric models with what was called a grand desert. So this is logarithmic in mass scale. Here's the Z and W boson. Here's the top quark. Then basically just by renormalization group evolution, you could get from here to here. And then if you made a study of this region, which is up to about a TeV, you could learn the unifying theory of nature. And so there are various ways that people expressed this a long time ago. This is a very interesting and complicated diagram that I found in the accelerator test facility hall at KK in Japan. Steven Weinberg wrote a book called Dreams of a Final Theory, which in a much more elegant way lays out this idea, and also all kinds of other interesting ideas Weinberg had about both particle physics and its political expression. Well, these were great ideas 25, 30 years ago. I think no one believes in them anymore. We really need to get more information from experiment and how we do it. So, what I'd like to say is that we really need to imagine now accelerators that can probe up to and beyond the 10 TeV scale in particle physics. Let me just say that in addition to the motivation I've given, there are two other interesting motivations for doing this. One has to do with flavor. There must be flavor-dependent interactions because the quarks and leptons have a spectrum of different masses.
I don't know that you've introduced the term flavor before.
Oh, I'm sorry. Flavor has to do with the different varieties of quarks and leptons. So up, down, charm, strange, electron, muon, tau. The muon over electron mass is 200. That's been known since the 1940s, and it's been a mystery since the 1940s, and it still is. If there's dynamics behind that, those particles should be around somewhere. The motivated mass is again in the 10 to 30 TeV range. It would be nice to be able to get there and really try and explore for these kinds of interactions. For dark matter, there's a lot of activity now about very light dark matter states. I think mainly ad hoc or based on various anomalies. But I think really the region that is very interesting to explore is well above what people have seen now. If you have a particle that couples more strongly to the Higgs section and is invisible or very weakly interacting, so it's invisible in a collider setting, the mass you expect is a few to 10 TeV. And it would be wonderful to do experiments that access dark matter particles in that region. And so with these motivations, let's just go forward and ask, what kind of accelerator technology can we have that will get us to these very high energies? So, as I said, that's the question. Now, the problem with this is that we're very confused in our community about how to go forward. Current particle colliders are close to the limits here in several directions. The LHC, the largest particle collider, that's already a 27-kilometer rig. It's enormous on the scale of scientific equipment. The cost is something like $10 billion, and it's not exhausted yet. What was proposed to be the next collider, called the ILC, the International Linear Collider, an electron-positron collider. This didn't have higher energy. In fact, the ILC only goes up to maybe at most half a TeV in the center of mass for electron-positron collisions. It has more precision, so you get reach that way. It's still 20 kilometers long, an $8 billion proposal, and to go significantly beyond that is very challenging. Electrical power has also become an issue, especially this year in Europe. People worry about it a lot, even here. These are 100 megawatt site power accelerators. The next generation, we don't want it to be a gigawatt. No one will allow us to build that. But also, as the energy increases, the luminosity, the collisions per second must increase. And so we're caught between wanting to basically increase the power of the accelerator in various ways, while being limited by size and electrical power, what we draw from society, on the other hand. Somehow, we can't make a next step without an improvement in technology. And I guess for me, that's what makes this subject interesting. Because the question is, what do we have to do? What do we have to invent or develop in order to take the next big step in particle physics? So let's say just a word about luminosity, because this is I guess even in the high energy physics community, there are people who need a lesson on this. Luminosity is given in units of events per centimeter squared per second. So a cross section is centimeters squared, You multiply that by the luminosity to learn how many events you're going to get per second. The typical, currently best performing colliders are getting 10 to the 34 per centimeter squared per second. So if you compare that to the QED point cross section, electron-positron goes to mu plus mu minus. That's your canonical new particle pair production cross section. As you raise the mass of what's on the other side, you have to go to higher and higher center of mass energies. The number is 100 femtobarns divided by the center of mass energy in TeV squared. So that turns out to be, for 10 to the 35 per year, 10 to the 5th events. Maybe that's a sample that you could really make a study of. But then it's divided by the center of mass energy in TeV squared. This goes down very rapidly. And so to explore the 10 TeV mass scale, you need something like 10 to the 36 as your criterion here. Maybe for proton colliders where you can produce things through QCD, 10 to the 35 is okay, but it's still extremely limited. And so at the same time that we're trying to raise the energy, make these accelerators smaller, make them more affordable in terms of electrical power cost, we have to continually improve the luminosity theory. Okay. So solutions to this are now proposed with proton, muon, and electron-positron colliders. And I'd like to discuss these in turn. So first of all, the protons. For each of these, there's going to be a slide that's called the unfortunate facts of life. So for protons, this is the most conservative approach, but there are unfortunate facts of life. One is that you would put protons in a ring, a large ring, a synchrotron, and the energy you can reach depends on the bending power of the magnets and the size of the ring. So 0.3 times R in kilometers times B in Tesla gives you the E in TeV. And so unless you can go to enormous magnetic fields for your bending power, you're restricted to being in very large rings. The LHC, we're talking about 7 to 8 Tesla in the magnets, 27 kilometers, giving you 14 TeV eventually. Of course, you can't put the magnets all together. There have to be some spaces between them, so even this number even gets at this. Number two, the proton is not an elementary particle. It's actually just a big bag of quarks and gluons. And it's the quarks and gluons that are making your basic particle production reactions. If you want to discover a new particle, you have to collide things that carry only a fraction of the proton mass. And so you're talking about so-called parton energies, which are 1/10 to 2/10 of the proton energy. And so you have to take that into account in evaluating how much you get per GeV in the proton-proton collisions. And finally, there's an issue called pileup, because as I told you, the point cross-section, the cross-section for producing new things, goes down dramatically. But at the same time, the proton-proton total cross-section is a constant. And even the cross-section for protons to have a reaction where you produce some energetic stuff basically becomes a constant as you go to higher and higher energies. So you have to fight that harder. As I say, still this is the most conservative. Here's just a warning about pileup. This is an actual event from Atlas where when the proton bunches pass through each other, you have in that bunch crossing 65 proton-proton collisions. And the blue are all the tracks that are produced. If you look very hard, you can see there are dots here. Can you see that? Probably you can't see that in the back. Little white dots. So those are where the proton-proton collisions actually occurred. And maybe I should say, this is a Drell-Yan event, which is to say, QQ bar goes to 2 muons. The muons are the yellow tracks. And so you have to understand this enough to measure those tracks with high precision in the presence of everything in blue. And maybe I should also say, people actually know how to do this. I mean, I don't know how to do it, but I think Andy Haas can probably tell you who can explain to you how this is actually done. It's already a big challenge. This will now go up by orders of magnitude as we go to higher. Okay, this is the one of two proposals on the table for a next generation proton-proton collider. It's called the FCCHH, the Future Circular Collider at CERN. The CERN laboratory is here, here. The blue ring is the LHC, already 27 kilometers. This is a 100-kilometer ring that goes under Lake Geneva and around a mountaintop called the Salève, which is down here. It goes through all kinds of complicated geology, I should also say. 100-kilometer ring, 16 Tesla magnets. This 16 is important. I'll come back to that in a moment. That gives you 100 TeV in proton-proton center of mass energy. That's now corresponding to something like 20 TeV in parton-parton center of mass energy. And the estimated cost is currently 24 billion Swiss francs. So it really takes you well beyond the cost of LHC by many factors. There's a similar proposal called the SPPS in China, and that would be a ring, again, of this 100 kilometers. Here's a work example. If you built this collider, if everything works well, if you can actually reconstruct the events, you can discover supersymmetric particles within this blue contour here, which, as you see, is about 8 TeV in the gluino, actually not yet the scale of the Dirac gluinos, and 30 TeV in the quark partner, because the quarks are a little more energy. This is the kind of thing one hopes for from this collider. Now, to keep the size within limits, high magnetic fields are needed. And actually, this needs a search for new superconductors. So the LHC is built out of niobium titanium wire, and this already maxes out at about 8 Tesla. With niobium 3 tin, 13 Tesla accelerator magnets have been constructed. The foreseen maximum here is about 16 Tesla. And that's the reason for the number that I put on the previous slide. So ultimately, that tells you for a certain energy how big your collider ring has to be, working with conventional superconducting technology. And maybe I should say this is a more difficult material, although actually there exist companies now that make large amounts of niobium 3 tin wire. I think ITER is the main customer for that application. The current cost is about 5 times LHC. And if you don't like that, you can go to high TC materials. And high TC materials allow even stronger superconducting magnets, but the current costs are something like 25 times the LHC magnets. So that gets scary, but of course you can say, well, if we have 20 years in the future, we can bring these to industry, have industry learn how to make them much more cheaply in bulk. We've got a lot of bulk because the thing is enormous, and so maybe that can succeed.
So is this the factor per magnet, and you have to multiply by the ratio of the lengths?
Yes. So here's a little map of these things. This is the current density versus the magnetic field. This is the line for niobium 3 tin. You see it really whips out at some level. These things here are various kinds of high TC. Here's, I guess, the highest magnetic field solenoid that I could find. Well, I think it's still true today. This is a hybrid at the High Magnetic Field Laboratory in Tallahassee, which actually uses YBCO and then various more conventional superconductors to augment that field. It gets you to 32 Tesla. This is let's just say it's not something you can buy off the shelf. In China, they're experimenting with the iron-based superconductors. This is a design from the study for the SPPS of an iron-based superconducting magnet with ports here for the 2 counter-rotating proton beams. This is a 12 Tesla design. The goal was a 24 Tesla dipole magnet for a high-energy collider that would take you maybe to, I guess, 150 T. And there's one more thing that you have to worry about, which is that Ordinarily, you don't have to worry about synchrotron radiation from protons. But when you get into very high energy, protons do have synchrotron radiation. And so you have to do something about that because synchrotron radiation can't impinge directly on a superconducting magnet. And so part of the magnet design has to be some beam screens, which I guess are here, to actually protect the superconducting, please excuse me. Here, this structure has screens that protect the superconducting magnets from the radiation from the proton beam. This works at 100 TeV. Remember, synchrotron radiation goes up like e to the fourth. So greater than 200 TeV, this may actually be a limit to it. Maybe if you had a high temperature superconductor, the limit gets less strong. So that we'll have to revisit. Okay, next one, muon colliders. The muon colliders are maybe more interesting than electron colliders because with a muon really is an elementary particle. So if you have a 14 TeV muon collider, you get 14 TeV that can go into the annihilation reaction, and you can produce 7 TeV particles. Similarly, 30, 15 TeV particles, etc. So this, in principle, sounds much more powerful. And in fact, I think a lot of my theory colleagues this year, and especially at this recent snowmass workshop, are very interested in this. So let's just talk about, again, the unfortunate facts of life. Muons are unstable with a lifetime of 2 microseconds. Of course, relativistic muons, you have time dilation working for you. So it's really just kind of the initial stages when you're trying to get the muons up to relativistic speed that you have to worry about manipulating. Muons are difficult to produce in the small phase space needed for acceleration. You can't just make muons. You have to make muons by colliding some kind of beams. So the approach favored right now is to take a proton beam and smack it into a lithium target, and then an enormous number of particles, including muons, come out the other end, also pions, which decay to muons. Those cover order 1 of phase space. And so you have to take a big bite of phase space, contract that in such a way that you can put that into a cooling system, which we'll talk about in a moment, and then use the cooling system to eventually decrease the phase space volume by a factor of 10 to the 6th. It's a severe challenge, and that challenge has been investigated over the past 20 years, and it'll be investigated, I think, a little more intensively in the next. And finally, when muons are guided to the collision point, they're still decaying. And so their decay products are also coming into the detector, and this is also something. So this is the approach which is most efficient in terms of electric power, if you can solve these problems and have it work at all. And I think people who are expert in this say this is kind of winning the race for now because of this criteria. But of course, you have to solve, especially these two very difficult problems. So the muon is an elementary lepton, as I said before. If you think of a muon beam, for example, in the LHC, that accelerator in principle would support a 14 TeV muon collider. For electrons, it just doesn't work. For LEP, already at 200 GeV, you're losing about 2% of the energy of each particle every time you go around. And that's just not sustainable, especially if you don't hide it. But for muons, you can deal with it. The improvement in terms of synchrotron radiation is a factor of 10 to the 4th. And so that you're winning. The cooling scheme, there are various ones considered, but this is probably the one that people are putting the most effort into. What you would imagine is you have a muon coming at, if you like, an arbitrary angle. You then have an absorber, which decreases the momentum of the muon. Then you have an accelerator, which increases the z component of the momentum. And in this way, you get the muons back to their original momentum, but you've basically decreased the transverse momentum. And so then you've contracted the phase space. A subtlety about this, well, there are two subtleties about this. One is that muons are notoriously hard to control. Probably some of your experimental colleagues in the audience have done experiments with muon beams, and you always have muon halo, muons escaping in various directions, which are very troublesome. Here you really need high efficiency in each stage of the cooling. And secondly, this is only decreases the transverse phase space. And so you have to be able to couple this back to the longitudinal phase space. And this is done by something called six-dimensional cooling, where you take the muons and you wind them in helices, which then redistributes the momentum between longitudinal and transverse components. So here is a design for a muon collider. Basically something that produces the proton beam, some extremely high intensity target, probably liquid lithium is what people prefer. You have magnets that capture that. You have many of these cells that produce the cooling successively. Something like 30 cells are needed, the muons passing from one to another. Eventually, when you can put these things, when the space is small enough that you can put it into an accelerator, you're kind of done. And then you do need a different accelerator size for every energy at which you're going to go. And here is from the SNOMAS Muon Collider Forum report, the phase space evolution of the muons. So from here, you first do transverse cooling, and then in various stages, you try and equilibrate between the transverse and longitudinal directions. Some of the stages here to produce the final product require 20 to 50 Tesla magnets, but those you don't need hundreds of kilometers of them. You just need some one-offs in specific places. Okay, this is the best that people have done in terms of phase-space compression experimentally with muons. There was an experiment at Rutherford Laboratory called the MICE experiment. They demonstrated 7% phase-space compression for the central 10% of the muon heap. So, well, let's say you need 10 to the 6th compression for a relatively large fraction of the muon heap. And it's going to take a lot more, even simulation, to build an appropriate cooling channel that can achieve that, even in 30 stages. Now, as the muons come into the detector, they decay. And the decay products are high energy electrons, which go forward, and they go into the detector region. So this is actually another problem. It's called beam-induced background, BIB. And to combat that, the detector designs have tungsten shields. Here, this is the beam collision point, and also here to collect energy from decays upstream. The problem with this, of course, is that no shield is perfect. A sufficiently high energy particle will punch through the shield. And so one electron goes in, and a ton of neutrons, gammas, and other things come out the other end. And so these are some simulations of the beam-associated background that you have at muon colliders. What's interesting about it is that most of it is out of time with the signals that you want to actually see as the physics events. Here, the time is occurring on the scale of nanoseconds. This is a blow up of this region. It shows that there's even more time structure inside it. So the way to combat this is actually, first of all, to use timing detectors within your accelerator. So right now, CMS is really making a serious effort to put timing in their tracker and even get down to the 30 picosecond level of timing individual hits in the tracker. And it's thought with that kind of technology fully developed, you could somehow get yourself out from under this enormous background. So assuming you can do that, the current state of the art is seen here. The blue is efficiency without beam-associated background in terms of particle PT, theta, and because we're talking about Higgs events that decay to heavy quarks, you have to recognize a vertex where the weak quark goes some distance, some number of millimeters from the interaction point and then decays. And you see from the blue to the orange a degradation of the efficiency due to basically this beam-induced background. Now, I should say 10 years ago, people did this exercise for the previous snowmass study of the US national program. And basically, they just threw up their hands. So I see this as enormous progress. But there's still a lot to be done in proving that this can be done in reality and really be able to get particle physics information. Muon colliders have one more unique hazard, which is that as the muons go around the ring, they're constantly decaying to neutrinos. Typically, the muon collider would be underground, but the neutrinos would come up to the surface maybe 10 miles that way, away from the accelerator. And if you just do this very naively, you find a dosage of a millisievert per year, which is close to the legally allowed dose for the general population. Now, let's just say, if you have to make a scientific argument to people that you're not irradiating, that is already a non-starter. And so the effort is to reduce this number to very close to zero. And the thought is that that can be done by wobbling the beam inside the accelerator. So basically, every time it passes a given point, it's at a different height, for example, within the accelerator. Then you can spread out the neutrino flux. So there's no one whose basement is going to get over-irradiated. But that's something that it's a unique thing that you have to worry about with muon. The other solution would be to build the muon collider in some remote place. For example, the Hanford Laboratory in Oregon, which is basically a 50-kilometer size radioactive waste dump. So that would be another solution. Okay, let's talk about E plus E minus colliders. I'm almost out of time, but please excuse me. The unfortunate facts of life here. Due to synchrotron radiation, circular colliders can't be used beyond about 350 GeV. So they are now out of the game. For linear colliders, this is a very important formula, that the luminosity is proportional to the power divided by the transverse size of the beam spot, which means that to make these machines affordable, you have to go to extremely small beam spots or pay a very high power bill. And finally, the E plus E minus beam-beam interaction becomes extreme above 3 TeV, and you really have to mitigate that and so forth. So if you can make this work, E plus E minus collisions are the simplest, the lowest background, et cetera, but the technical challenges here are extremely daunting. Number one says that you really have to go to linear acceleration rather than a synchrotron. And that means you have to pack more acceleration into the particle. For a linear accelerator, let me just take the example of ILC at 500 GeV. We have a luminosity of 2 × 10⁻34 from 10 megawatt beams with a 500 × 6 nanometer square spot size. So scaling to a 30 TeV collider at 10 to the 36, you can keep the 10 megawatt per beam if you can make the spot size a fraction of a nanometer in both directions. So let's just say this is a little beyond the state of the art. Maybe after we run a linear collider to do the Higgs boson study, we'll know more about whether these parameters are reachable. In a linear collider, the beam must be constantly replenished, and the efficiency of converting the power you draw from your electric company into beam power is really a crucial parameter, so that comes in. That's one of the reasons that the ILC is a superconducting linear accelerator rather than ordinary. Although, as I'm going to show, it doesn't quite get you there. The ILC is 31 MeV per meter, so it takes a lot of meters to get to 10 T. So what we need actually here is genuinely new ideas about electron acceleration. For those of you who are curious, there's something written for the European Strategy Study by the Allegro collaboration, Crow et al. And it's an interesting paper. Although I think the leaders of the European Strategy Study decided that this was too far out for immediate consideration. Nevertheless, for the future, maybe it's interesting. One approach is called dielectric laser acceleration. It's interesting that a laser beam has fields in it which are hundreds of MeV per meter. So if you can actually use those fields to accelerate particles, you might be in business. And so one way to do that is to bring in the laser beam from the side into a dielectric structure that can then hold essentially visible light or near infrared light in small cavities. And so you see that in this slide. You can see here a set of cavities in the dielectric. The laser beam comes in from the side. Here's the geometry for bringing in the lasers. This is called, by Bob Beyer, this is called accelerator on a chip. The design has 10 parallel channels, 3 times 10 to the 4 electrons per bunch, and it does reach this high luminosity when you kind of add everything together. An alternative, which I'm very interested in, which we're really pursuing now at SLAC, is something called plasma Wakefield acceleration. So what you want to do there is use a channel, a cylinder which has a dilute plasma in it. Put some kind of electromagnetic pulse through this channel. And in that way, you can generate very high fields. So here's an illustration of that. You have the plasma, you take either a laser pulse or an electron bunch from an upstream electron accelerator, an intense but low energy, let's say GeV, electron bunch. As it goes through the plasma, it opens up a space, here it says 0.1 millimeters, where the electrons are driven out, and these spaces have strong longitudinal accelerating fields. And so then what you can do is then put a trailing bunch through this to be accelerated by those fields. And roughly, your cavities are, let's say, this long, or maybe a meter long. The trailing bunch will go through a succession of these cavities and therefore achieve very high. Sorry?
Are you gonna finish?
Yeah, I'll finish very soon. You have to worry about energy efficiency, reproducibility shot to shot. Oh, maybe I should have said, there's a number here somewhere. Oh no. I left out an important slide, which is, oh, yeah, no, it's here. This method naturally produces very high gradients. Gradients of 150 GeV per meter have actually been observed, at least anecdotally. There are papers which give experiments where, in a controlled way, you can produce 4 to 5 GeV per meter. So that's now going really well beyond all other accelerator techniques. Although the problems here are that it's not under control yet. And a lot more research is needed to make one of these accelerators that can actually maintain small emittance, good properties of the beam over kilometers of acceleration. Okay, another problem with E plus E minus colliders is the very small intense spot sizes. So in the bunch-bunch collisions, you have high electric fields, synchrotron radiation, and then the problem that you basically degrade the beam in that process. So I think I have a kind of just hot off the presses example of this. For round beam collisions, so this 0.6 by 0.6 nanometer spot, the nominal energy is here, but the beam-beam interaction spreads the energy of the colliding electrons down to very low energies. You can somewhat ameliorate this with flat beams, but still, these low energy particles really do affect the structure of the beam. Both of these designs, I think, have a luminosity of 0.5 times 10 to the 35. So in principle, you can get there if you can make the electrons survive what's being done to them in the bunch-bunch collision. And there are various ways to ameliorate this that maybe we can talk about. All three of these approaches require really much effort to reach the 10 TeV scale. We really need to engineer again for power, cost efficiency, higher luminosities. There are many degrees of freedom that have to be pushed, and not so much room to push them, but what shall I say? This is now the next 40-year crusade. And as high energy physicists, we really believe that we have to get there. So I hope you'll support us in this. Be interested in this program as it develops, probably over decades, and that interesting things will come out that will be relevant experimental tools for other areas of physics. So can I show one more slide? Okay. Okay, I just want to, I found this in the New York Times archives, and it has a very interesting lesson. This is from March 1953, the announcement of a unified theory of nature by Einstein. And I don't know how many of you have read Einstein's little book, The Meaning of Relativity. And in the appendix, there's a unified theory of the non-symmetrical field. What Einstein was trying to do was to unify gravity and electromagnetism and claim that that would be a theory of everything. And of course, that was doomed to failure because already at that time, the strong interactions were known. The weak interactions also, one had a lot of information about. But Einstein somehow was frozen in his mind. He wasn't interested in that. He wanted to solve only this problem, and he thought that would bring him to the ultimate solution. So today, we have people who take the standard model, unify it in some way, and claim that that's the final solution. But they're probably just as wrong as Einstein was at this time. To get beyond this, we need more experiments. We need these experiments. And so somehow we got to get there. And so that's what it is.
Hard for theorists to get this much press.
Well, just win the Nobel Prize.
So I heard for the first time about the Wakefield when I was a student, so that's well 40 years, so I hope that this time scale is 40 years. But so to go back to the Crusades, their stated goal was a miserable fiasco, right? When they didn't achieve it. They achieved other goals, more or less objectionable, but their success was in changing the goals, if they had any. So, I mean, it's should we think about also the possibility of changing the goals here, of building an accelerator that does other things that can be used for small-scale experiment or for other purposes?
Well, we're always asking that question anyway, because every technology that I've discussed has a development scheme, and the development scheme has other applications. There's an accelerator that I've gotten involved in this year, which is a solution not for the next, but for the next, which is called the C-cubed accelerator. It's a one collider approach to building an E + E - 6 vector. And there we see that that program allows you to, for example, build. So the idea of that program is to improve the accelerating gradient of warm accelerators from 17 MeV to something like 100 or 150 MeV. Okay, if you could do that, you could make much more compact medical accelerators so they would be affordable by many more hospitals. You could have university-sized free electron lasers. Instead of having people always go to SLAB to do their free electron laser experiments, they could have a dedicated facility that they could run themselves 24/7. So there are applications as you develop this technology. And the question is, you have to keep all these goals in mind. But I think the most bold accelerator physicists, this is the goal they have. So to keep those people interested, this is what they need to do.
Andre?
How does LHC use all this 100 megawatts?
Well, there's
What do they do with all this power?
the superconducting magnets and the cryogenic system.
But if magnets are truly superconducting, they don't require any power.
No, a superconductor runs current without resistance, but when you have a magnet, you have to drive a current through it. And it actually is dissipated in a certain way. And then, of course, the power is deposited at 4 degrees Kelvin, or actually 4 degrees Kelvin. And then you have to propagate it out to room temperature, so that is also a very inefficient process.
I don't understand. So the current has no resistance, correct?
No, the current has resistance in the presence of the magnetic field, the flux lattice.
or at a finite B, there is
Yes,
actually a
yes.
resistance.
And so you
So it's
actually have
really
to-
ohmic heating, you just dissipate it into heat?
So, so you have a small heat load at 4 degrees Kelvin. But then when you try and transfer that out, that process also is inefficient. And then, of course, there's the whole cryogenic system to have, kilometers of superfluid helium at 4 degrees
So
Kelvin.
it's
which is-
cryogenics.
Yes, the cryogenics is very powerful.
Final question.
How long would this take? I mean, if we manage to have some technology, the estimation in time, 40, 50 years, 60 years?
The one for which there is actually a machine design is the Large Circular Hadron Collider. So that they're talking about, in principle, the earliest it could come, if CERN made that its next goal after LHC, is about 2050. And
2050 or 30.
50, yeah. Now, however, if you, as the plan is, you want to build an electron collider in that tunnel first, then that pushes it back another 20 years.
2070 if you do
Yeah.
plus or minus.
But also, isn't you built in a very long run of the high luminosity LHC?
Yes.
But maybe that's a mistake.
Well, that's.
What do you think? I mean, I'm asking, do you think that would, because if you want this in your lifetime, maybe you don't want it
Yeah,
happening.
but the problem is that the cost of these magnets is untenable now. We need a D program to industrialize the magnet technology, even for 16 Tesla. And it's thought that you won't actually know the cost of the magnets until the mid-2030s. So you can't
You
bring
might
it
as
too
well
much
run
closer.
the high luminosity LHC
Yeah.
to bide your time while
Right.
you get this developed.
But there is not a way to bend the trajectory of these particles, like crystals, for example. I know that there was this idea of channeling the trajectory into crystals.
Yeah, but I mean, that's a low luminosity collider.
Yeah.
Crystal channeling is very inefficient. And here, it has to survive 24 hours of turns. But people talked about this in the 1980s.
Yeah.
I think it didn't go anywhere.
Okay, no more questions? Let's thank Michael. There's a reception in the 8th floor CSMR space where we can talk more with Michael.